Welcome back to Masters for Operations 2. We were discussing on crystallization. Now we will be discussing on the solid liquid phase equilibria and theory of crystallization. Okay, so before entering into the solid liquid phase equilibria, we should learn the terminology supersaturation. So that is, we can say, quasi static state of one solution, where we can say the capacity of the solute inside this solution is exceptionally higher than the regular solubility limit. That we can say, if we have a supersaturated solution and a few crystals are dropped into it, a driving force for the transportation of the solute from the bulk of a solution to the crystal surface comes into the play. Okay, so thus the extent of supersaturation is the driving force actually for the crystallization. Okay, it may be mentioned that the solubility of the very small particles may be significantly larger than the normal solubility of the substances, that is given by this Gibbs-Thomson equation, that is ln C by Cs is equal to 2 into sigma into mw by RT into rho c into r, where C is the, we can say, solubility of the particle of radius r, where Cs is the normal solubility. So, this additional solubility actually comes into the picture when we have this very teeny particles. Okay. So, whenever we will be discussing about the solubility curve of this any salt or any organic materials, then we discuss this one, the solubility of the regular crystals. But whenever the regular crystals are converted into small particles, then their solubility level actually increases, and that is why we can say in a particular temperature and pressure the solubility actually increases from the regular solubility, and due to that at a constant temperature and pressure the capacity of the solvent to dissolve the solute increases, and that is why the supersaturation is created. And where sigma actually is the solid liquid interfacial tension, mw is the molecular weight of the solid, and T is the absolute temperature, and rho c is the density of the particle. Okay. So, we can say this one, since the smaller particles have more than normal solubility, these dissolve even in a saturated solution. That is why we say in a saturated solution, we can say saturated solution means the maximum amount of the solute is present at that particular temperature and pressure, and raise the temperature, creating this supersaturation. Okay. So, larger particles then starts growing, and overall process consists of dissolution of the smaller particles, making larger particle grow. So, this phenomena is called Oswald ripening, or we can say this one, this way the particles will be associated in all three directions, in all x, y, z directions, and then we can say this one big crystal will be formed. In crystallization, equilibrium is attained when mother liquor actually is saturated, and equilibrium relationship is represented by the solubility curve. So, whenever we have this suppose feed, and say when it is supersaturated in a particular temperature and pressure, so we say this is the magma. Whenever this from this magma this crystal is separated, then whatever the exhaust fluid will be there, that we say that is the mother liquor. So, there we can say this one solubility of the solute will be there at the temperature and pressure, but due to this supersaturation, this more amount of the solutes will be present inside this solvent. That is why sometimes we get less crystal yield, also we will be discussing in detail that in the regular cases. So, now this one, whenever we will be discussing about the say solid liquid phase equilibria, if it is a pure this one solvent solute like this any salt or any say sugar or any type of organic materials, then with increasing temperature in general we can say this solubility increases. That is why whenever we put this, if we draw this temperature and say solute concentration, then we get or in general we get this linearly increasing curve. So, that curve, above this curve we can say that is the unsaturated one, and below this one the saturated, and whichever is excess that will be coming out as the say precipitate. or we can say this one solid phase. Okay. So, below this one we can say this one saturated and excess amount is separated as the solid phase, and above this one it will be remain in the unsaturated condition, and the on the curve actually we can say this one saturation point is there. But whenever we have the mixed solid mixture, then in general we do not have that simplicity and their solubility curves are more complicated. If we take the example of say benzene and say naphthalene, then we can learn that in case of that type of two solid mixtures, their solubility curves are actually not linear or not simple. Like this, if we start from this A to E to say we can say this to B. So, this actually we can say this is a solubility curve for this benzene and naphthalene mixture. So, we can say this one in this x axis, this naphthalene concentration is increasing in the right hand side, or we can say this one benzene concentration is increasing in the left hand side, and temperature is increasing in the y axis. Okay. And so, that is why you say in any point on this curve we can say this one on A, E and B. So, any point we can say this is we can say this one solubility point, or we can say saturation point, or we can say saturation concentration of naphthalene in benzene at different temperatures, or the vice versa. So, that is why we say this is the solubility curve. But you see this one, this solubility curve is not simple like any other solubility curve. Here you see this one say this lowest point is there, the below this one we can say this one any of the mixture will remain in the solid condition. But this the thing is that say if we start from A to E, there we can say this one when the benzene concentration is more, and say suppose in this zone actually we can say this one from A, E and C, this zone we can say this one whenever we will be decreasing the temperature, then we will be getting that say solid benzene will be separated because that is in the huge amount, and the solution will contain this naphthalene. But whenever we will be talking about this right hand side, suppose in this zone in between say B, E, D, there you see this one if we decrease the temperature we will be getting this solid naphthalene and this benzene in the solution, because this benzene concentration is lower here, and this the arms actually are called this liquidous curve. So, this one suppose A, E and E, B, these are called all liquidous curve. Okay. So, above this one, above this curve means A, E, B, these are all we can say this homogeneous solution, or this is we can say this one unsaturated. Okay. So, this is unsaturated because in that zone this the solution actually will demand more solutes to be dissolved as the temperature is very high, and below this curve we can say this one these are all saturated, and we can say this one based on the composition the few amount of the solid will be separated from the solution mixture, and whenever we will be talking about C, E, D below this one in any of the compositions we can say, and at that temperature always these will be in the solid form. Okay. So, in this zone these are in the solid form. Now, you see if we start from point P1, say suppose one will be this one more than say 20% naphthalene concentration, and one will be discussing about the less than 20% naphthalene concentration, or we will be discussing one composition where naphthalene is more, we will be discussing one composition where benzene is more. Suppose this naphthalene is more, this is the composition like P1 and temperature is 60 degree Celsius, and we are decreasing the temperature and keeping the pressure constant, and then when it will be reaching point P2, then we can say this is the saturation point, means above this one it was unsaturated one, that is why it was homogeneous solution. So, whenever it will be reaching point 2 it is saturated, it reaches the saturation point. Then we can say this one again if we decrease the temperature then it will follow this route like this, it will be following this route, and temperature as temperature will be decreasing, then composition of the mixture will be decreasing, means this excess amount of the naphthalene actually will be coming out as the crystal. So, that is why naphthalene composition will be decreasing and it will be reaching one point that is E. So, this is, so we can say this one at around say minus 5 degree Celsius, it will be reaching where we can say 20% naphthalene is there and 80% benzene will be there, because the remaining amount, say if we say it is a 65% naphthalene was there in the beginning. So, now it is only 20%. So, the rest amount actually is separated as the crystal. Okay, so that is why we can say this one, it will be following P1 to P2 to E. So, okay, so that is we can say this one, and then this is the we can say this one minimum point where we can say this one all the phases will be coexisting, means a solution means a phase will be there and solid phase also will be coexisting. Okay. And if we take the one composition where benzene is more and say naphthalene is less, suppose say if we take the composition like 10% say we can say naphthalene and say 90% benzene is there. So, mostly it is benzene. So, whenever it will be reaching this point P4, then it will we can say it is a saturation point. Then if we decrease again the temperatures, then it will go to this point like this, we can it will follow this path from P4 to E, it will be coming, and then at that time what will happen, this benzene will be separated. That is why this we can say naphthalene concentration will go on increasing, and then when it will be reaching point E, then both whatever the residue was there means in the solution, that will be now these all these solids will be separated from the system. Okay. So, this point E actually we can say this one called eutectic point. So, this is we can say this is the lowest equilibrium solidification point possible for any solution. So, whenever we have this eutectic mixture, then that is we can say this is the lowest equilibrium solidification point. Okay. So, complete solidification of the solution occurs when the solution represented by point E, that is there in that composition it is cooled. So, complete solidification will take place, and that time it will not follow any of the we can say routes like this like P2 to E or P4 to E, like this it will not follow any solubility curve or saturation curve. So, there actually we can say the entire composition will be converted into the solid crystals. Okay. And we know that say below this whatever the composition is, it will be solidified and then crystal will be separated, that actually from this we can say equilibrium curve this one expect. Okay. So, now we will be discussing about the yield of the crystallization process. So, this is very important parameter actually for the crystallization, or if we say this crystallization is efficient, then we need to calculate the yield like this. In many industrial crystallization processes, the crystals and mother liquor are in contact long enough to reach the equilibrium. So, and the mother liquor is saturated at final temperature of the process, that is at the constant pressure. So, the yield can be calculated from the original concentration, say means that is in the unsaturated condition, whatever the original concentration was there, that will be definite, and the solubility at that final temperature. That is whenever the temperature is decreased, then what is the final temperature, and then at that temperature what is the solubility limit, and what was the initial concentration. So, from this difference actually we will be getting how much amount of crystal actually is separated. So, in the beginning what was the concentration and at that time what is the solubility, that is not so important, because that is we know that at the higher temperature it will remain in the unsaturated condition. Okay, but the original concentration is required, because the remaining amount will be separated as the crystal. Okay. So, if this one appreciable evaporation occurs during the process, this must be estimated. So, whenever this some amount of evaporation takes place, then we can say the water amount actually will be changing from the original solution. So, that needs to be considered, and based on that this if the some amount of the water is evaporated, then yield actually will be increasing. So, in any process if there is evaporation, yield will be more. If there is no evaporation, then yield will be less, because that time the we can say the total amount of mass which will be separated, that will be lower than whenever the mass that will be separated if some amount of water is evaporated, because you see solubility is dependent on the temperature and pressure, and say this one in a particular temperature how much amount of solute is present per unit mass of the water or solvent. So, that is why we can say evaporation, if evaporation is there, we need to consider this one, means whenever we will be doing say water balance or solute balance, then we need to consider this water amount also. When the rate of crystal growth is very slow, then little crystal surface is exposed to the saturated supersaturated solution. So, that is sometimes required to add the, we can say, foreign particles, or we can say this one solid interface where the crystallization process will be enhanced, where this process is very slow. But hence then final mother liquor may retain appreciable supersaturation and actual yield will be less than the calculated from the solubility curve. That what actually we tried to explain, that due to the supersaturation in a particular solubility limit in a particular temperature, the mother liquor will contain more amount of the solute than its solubility limit. That is why the actual yield will be lesser, that will be calculated from the solubility curve or saturation curve. Now, we will be solving one problem, that how the yield actually is calculated in case of this water evaporation or without water evaporation. This is a very simple problem like this. A solution of 38% magnesium sulphate is cooled to 15.6 degree Celsius. So, initial temperature will be definitely the room temperature, and we assume that this at room temperature whatever 30% magnesium sulphate is there, that is unsaturated solution. And what is the yield of this magnesium sulphate 7H2O? We need to calculate this one. So, solubility is 24.5%, that is in weight percent actually at 15.6 degree Celsius. Original mixture is 1000 kg. Now, we need to assume that there is no evaporation, water evaporation, and we need to consider when 5% water is evaporated. So, in the beginning what we will be doing, say we will take the, suppose feed is equal to say 1000 kg, okay. Then xf will be say 0.3, then xw will be 0.7, this water, because in case of the crystallization water has a role also, we need to consider that also, okay. And say in this we can say solubility, this one at 15.6 degree Celsius is this one 24.5. So, it will be converting from, so mother liquor will contain 0.245, this one x mother liquor will be 0.245. Okay. So, now what we will be doing this one, so we need to calculate this say molecular weight, we can say this one molecular weight of MgSO4. So, that is we can say 120.4, and molecular weight of FgSO4 7H2O will be 120.4 plus 126, that will be say 246.5, that is okay. So, this water molecule is 18 into 7 126.1. So, we will be doing this both water balance and say the magnesium sulphate 7H2O balance for this system. Suppose for the first case, let us take this, no water evaporation is there. Suppose for case A, we will take this one as this, we can say cooler and crystallizer say. So, feed is F is equal to say 1000 kg and xf is 0.3. Now, it will be converting into 3 different streams. Okay. So, firstly like say we can say C kg say crystal, okay. Then it is S kg mother liquor, and so suppose W kg water. So, for first case this W is equal to 0. So, first case actually we can say W is equal to 0. We will be doing that say water balance. Water balance we will be doing, suppose F x W is equal to S into x s plus say C into x c plus W into say x, let us take evaporated. Okay. So, F is equal to say 1000 kg into x W is equal to 0.7 that S we do not know, S into X S is equal to, we can say it is we can say crystal will be say 24.5% is crystal is there, and that is why say the remaining amount will be there. So, 100 minus 24.5, that is we can say 75.5 divided by 100, okay, and plus say crystal will be say, for this case also water will be 7H2O, and that is say 126.1 divided by say total is 246.5 plus water is equal to 0. Okay. And say if we do MgSO4 7H2O balance, then we will be getting this one, say F XF. So, 1000 into 0.3 is equal to S into the rest amount, we can say this one, this means this solid 24.5 in the mother liquor divided by, we can say this one 100 plus say C into remaining amount, we can say this one 120.4 divided by 246.5. Okay. This plus in evaporated there is nothing. So, we have now this, suppose this is equation 1, this is equation say 2. So, from this equation 1 and 2 we can say, if we do the say manipulation, we will be getting from, we can say this one from equation 1 and 2, we will be getting say S is equal to, so we can say 773.66 kg. So, that is we can say that is the mother liquor and crystal, that will be equal to the remaining amount say 226.34 kg say crystal. When there is no evaporation, then we will be getting 226.34 kg crystal and 773.66 kg mother liquor. So, that will be divided into two parts and W will be 0. But whenever we have the 5% water loss, like this we can say this one 5% water evaporated. So, then we have this. So, for water balance we can say this one, we will be doing then water balance, we will be doing the water balance like this, say F into XW, that is we can say this one 0.7, that will be S into like this whatever water, this 75.5 by 100 in this mother liquor, plus in crystal water will be like this 126.1 by 246.5 plus say this one, the total water actually was there like this for this case, out of this 1000 kg, this out of this in this feed 1000 kg feed, water was actually 0.7 into 1000 kg. So, that is we can say 700 kg. Okay. So, this is actually 700 kg, the out of this 700 kg 5% is evaporated. So, 5 by 100 into 700. So, that is we can say this one, that we can say equation 3, and we have this equation 2 like this 1000 into 0.3 is equal to S into 24.5 by say 100 plus C into 120.4 divided by 246.5. So, that is equation 2. So, from these two equations we will be getting now, say if we just manipulate these two equations, we will be getting that C is equal to 261.6 kg So, crystal and mother liquor will be equal to 703.4 kg mother liquor. So, whenever there will be evaporation, we will be getting more crystal, or we can say the yield is more. So, in case of this without evaporation, that was only 226.34 kg crystal. Whenever only 5% water is evaporated, then it is increased from 226.34 kg to 261.6 kg. So, that we can say this one, when the evaporation is there, we will be getting more yield. Okay. Now, we will be discussing about the mechanism of crystallization. So, this the formation of the crystal actually from the solution involves these 3 steps. The first step is this, we can say the supersaturation, how we can make the supersaturation. Then the second step will be nucleation, means a nucleus formation. Then we can say the third step will be crystal growth. Once crystal growth is complete, then it will be separated from this mother liquor, and means this one from this feed, and we can say that will be separated, and that will be say purified, cleaned, dried, and then it will be used for the final application. So, the supersaturation whatever we discussed till now, that can be achieved by the following methods, like this evaporation of the solvent from the solution. So, if we evaporate this one, then supersaturation will be created like this, that is one way. And another one is the cooling of the saturated solution. Just if we cool down the saturated solution, then also, or sometimes by cooling and heating like this in a cyclic order. So, whenever we will be first we will be heating, then we will be cooling, or then again heating and cooling, that way also we can say this one supersaturation will be created. Because whenever we have this big crystals, or we can say this one big materials, their solubility will be low, because the solubility also is dependent on the specific surface area. Whenever we are converting this into small particles, then we can say the solubility will be increasing. Okay. If we cool down, then we can say this one, if we cool down the saturated solution, then supersaturation also will be created. Or sometimes addition of a substance like this, which is more soluble in solvent than the solid, to be crystallized, then also supersaturation also is created. Then we can say this is a nucleation, that is a nucleus formation. So, that is we can say the worth of these very small bodies of the molecules are called nucleation or nucleus formation. Some clusters may become so big that these may arrange themselves in the lattice arrangement. So, in the beginning also we discussed that crystallization is one repetitive process, that it repeats the unit crystals in all 3 directions, in x, y, z directions it repeats. So, we can say this one in the lattice arrangement actually it will be added, and these bodies of this what is called aggregates actually are called embryo. Okay, these embryos are unstable and these may break into the clusters again. This stable structure together form a nuclei. Once this nuclei is formed, or we can say the nucleus is formed, then we cannot stop this, we can say crystal growth like this, then crystal growth starts. So, every crystal is surrounded by a layer of liquid, that is we can say this one as the stagnant layer. Once the crystals are formed, the nuclei formation stops and crystal growth actually begins. So, from the bulk solution, a solute particle diffuses through the stagnant layer and then reaches the surface of the crystal, and then all the surfaces, these are all we can say these combines and then form the big crystal. So, now we will be discussing about the theory of the crystallization. So, when the crystallization starts in a homogeneous mixture, a new phase is created. Okay. So, the basic steps of nucleus formation or nucleation and crystal growth are overall crystallization process. Okay. So, in the beginning we have this we need to make the supersaturation by any means, then we can say this one we have the nucleation, and then once nucleation is done, then crystal growth will be there. The combination of the nucleation and crystal growth is called this crystallization process. Okay. So, nucleation means the formation of these teeny new crystals in a supersaturated solution. a new crystal thus formed is called this nucleus. Then in this nucleation is of two types, one is the primary nucleation, another is the secondary nucleation. Okay. The primary nucleation is of also two types, that is, sometimes we have this homogeneous nucleation or sometimes we have heterogeneous nucleation, and for a secondary nucleation there are four different types of nucleation like this: contact, then shear, fracture and then attrition. This, either of these four different types of the secondary nucleation processes are available there for the industrial applications. Okay. So, now we can summarize this one like this: a nucleation process like this, primary is there and secondary. Primary is the homogeneous and heterogeneous, and secondary is contact, shear, fracture and attrition like this. In primary nucleation, we can say that it is the phenomena of the formation of these new crystals that is independent of the presence of other crystals in the medium. So, that is primary. By any means we can say this one new crystal is formed, or we can say this tiny surface or we can solid surface is created without the addition or without the help of any other solid surfaces. It is of two types like this, homogeneous and heterogeneous. In a homogeneous solution actually as a result of rapid and random fluctuation, molecules may come together and associate into a cluster. Okay. And the rate of this homogeneous nucleation this from chemical kinetics is given by like this. You can write this one, this B prime, this is equal to say A prime into minus 16 pi sigma cube into V m to the power 2 divided by 3 k cube t cube into ln s plus 1 whole square. Okay. So, where this S is equal to, actually we can see this one, S is equal to C minus C s, that is the we can say driving force by C s, and if we just manipulate this one is equal to C by C s minus 1. So, this S plus 1 will be equal to C by C s. If we take logarithm in both the cases, then it will be like ln S plus 1 is equal to ln C by C s. Okay. So, here we can say this one B prime actually is called say nucleation rate. So, that will be we can say this number per meter cube second, and this A prime actually, that is we can say this a constant, that is you can say system dependent, and this V m actually is we can say this one volume of molecule. Then this K is Boltzmann constant, okay, and T is this we can say this absolute temperature, and this S is we can say this one degree of supersaturation, how much supersaturation is there, that is a S. We will be solving some problems, then we will be clearing this one, and C is we can say solubility, and C s is actually normal solubility, that is we can say that whatever we will be getting this C s, that is from the graph, and this C actually is we can say this C, that is we can say this one during this supersaturation what is the solubility, that is much more higher than the C s value. Okay. So, the formation of the crystals of a solute in tiny suspended foreign solid particles or on the surface of the crystallizer is called this heterogeneous nucleation, and the rate of this heterogeneous crystallization depends not only the supersaturation, but also the availability of the active sites. So, how much active sites are present for the we can say the nucleation, that also controls the heterogeneous nucleation. Okay. Now, whenever we will be talking about the secondary nucleation, the formation of the new crystals actually from the existing macroscopic crystals in the magma actually is called secondary nucleation. So, for that we have these four different types of nucleation. The first one is this contact nucleation. It is the most common type of nucleation in the industrial crystallizer. The major steps are like this. First step is the generation of the cluster of molecules near or at the crystal surface like this, we need to generate the cluster, then the removal of the cluster, then growth of the cluster to form the nucleus. Okay. And for that actually we can say a simple power law nucleation correlation actually used to calculate the overall nucleation rate, like B prime is equal to that is we can say T into W to the power we can say m into m to the power n into Sp, where we can say this one B prime is the we can say number of nucleus formation, and W is the we can say this is a measure of the mechanical agitation, and Mt that is we can say this is total mass of the crystal per unit volume, and S actually is the this one degree of supersaturation. Then this m, n and p, these are all different exponents, and it is also we can system specific, and say k prime actually this is we can say this one k prime, that is the temperature dependent coefficient. Okay. So, that is also the system specific. Now, there are two different theories actually for the crystal growth. These are widely accepted. One is this mass transfer, this is mostly accepted theory, and second one is McCabe delta L theory law. The first one is this mass transfer theory, that is in this theory we can say this one, it is assumed that there are two steps in the series in the growth of the crystals, like this. First step will be like convective transport of the solute from bulk of the supersaturated solution to the surface of the crystal. So, that is convective transfer is taking place from the bulk to the crystal surface. Then second one is the surface integration or accommodation of the solute molecules in the repetitive way actually in the growing layer of the crystal. So, this mass transfer theory combines the diffusion and reaction processes and is called this diffusion reaction theory of the crystal growth. Okay. And the rate of the increase of the mass of the crystal, that dmc by dt can be written as this dmc by dt is equal to small k L into AC into C minus Ci, that is equal to k R into AC into Ci minus Cs, where this we can say this one we can say this one in the individual mass transfer coefficient can be replaced by overall mass transfer coefficient by like this dmc by dt is equal to k L into AC into C into Cs, where this k L is just by we can say this one overall mass transfer coefficient is equal to k L, that is k L is equal to we can say the mass transfer coefficient, and k R is equal to we can say rate constant for the surface integration divided by small k L plus k R. Okay. So, there MC is the mass of the single crystal, then AC is the area of the single crystal, k L is the mass transfer coefficient, k R is the rate constant, and C is the bulk solute concentration, Ci is the solute concentration at the interface, then Cs is the saturation concentration, and capital K L is the overall mass transfer coefficient. So, from this equation we can say what is the rate of the crystal growth, that we can calculate from this equation using either of the in terms of individual mass transfer coefficient or in terms of overall mass transfer coefficient, where actually we can say this one k L actually is represented in terms of individual mass transfer coefficient as well as the mass transfer rate constant. Okay. So, alternatively this growth rate can be expressed as the rate of the change of the characteristic size also, that is L of the crystal. So, that is very simply done by using this we can say this size factor, or we can say this one length factor, or like this. So, where we can say we will be writing this way like this MC, that will be say we can say rho C into this phi C into L cube, that we know already that AC is equal to phi A and L square, and Vc that will be like this phi V into L cube. Okay. So, now we have this dmc dt, that will be equal to we can say this one d by dt into we can say MC will be converting into say rho C into Vc, that is equal to we can say this one d by dt into we can say this one rho C into Vc is equal to phi C into L cube. That is we can say this capital L into say phi a into say L square into C minus C s from the previous equation, or we can say this one 3 into say rho c into phi v into L square into dl dt, that will be equal to capital K L phi a L square into C minus C s. Just by manipulation we are getting this one, and there actually we can say the growth rate, we can say L minus L s by T, that will be nothing but dl by dt, that is equal to K L phi a L square into, okay, so that is phi a into say C minus, so that is C minus C s by C s, that will be equal to, we can say this one small k s, where we can say this one small k, that is we can say we are getting this one is equal to small k into C minus C s by C s. Okay. So, that also we can say small k is coming from this part k L into this phi a. Okay. Then we can say this L s is seed size and G is measure of crystal growth. Okay. Therefore, k we can say this one small k will be like this, capital K L into phi a into C s by 3 into rho c into phi v, and s will be C minus C s by C s. Okay. So, we can say this one now we can get this G, that is will be equal to say dl by dt, that will be we can say this one k prime into C minus C s by C s into to the power q, that will be we can say k prime into we can say s to the power q. So, this just we can say this one small k and say k prime, these depend actually depend on we can say like temperature, then environment like this, like we can say this how much agitation actually is taking place, then we can say this one crystal geometry, what type of crystal actually is there, whether body centered cubic or face centered cubic or hexagonal close packing. So, crystal geometry like this, and then we can say finally crystal size. Okay. Crystal size also is we can say the controlling parameter. Okay. So, then the second one, that is we can say this one McCabe delta L law, there actually we can say this crystal growth rate G is independent of the crystal size L. So, that is why we can say this one del dg by dl, that is equal to 0. So, all systems do not obey this McCabe delta L law. In this solution actually, in case of this McCabe delta L law, both nucleation and crystal growth depend upon the supersaturation, but rate of this primary nucleation is very slow and rate of the secondary nucleation and crystal growth are linear in the supersaturation. So, now at the end of this discussion, we can differentiate between this crystallization and precipitation like this. So, this in precipitation, that is we can say this one is the solid formation from the solution by rapid and simultaneous nucleation, crystal growth and agglomeration of the particles. Okay. But in case of the crystallization, whatever we have learned till now, that say whenever we have this supersaturation, then we will be getting this nucleation, then we can say crystal growth. Okay. So, thank you very much. In the next class, we will be discussing about the design of the crystallizer and crystallization equipment.